What you see here is really a meeting of printed electronics and 3D printing. So on the one hand, the item itself is printed, so you have a shape, a structure, and then within that you've got the electronic traces, the conductive traces rather, positioned so that obviously you can see here this is the beginnings of a thermometer. And one of the questions is, how much of a product can I print? Well, so you can print that structural part, and you can start adding in that functionality as well. So you'll see these traces all the way through to the tip, and the item being ready here for an LCD display to be added into that item. So this is really merging those two worlds of 3D and non-3D. This happens to be a sort of a planar circuit within an object, but you can of course also print the circuitry as a spiral, which we'll look at in a moment. So one of the shapes that's really exciting in the world of electronics is coils and spirals, and that's the world of motors. It's beginning to look at things like capacitance or in this case, an electromagnet. And what we're looking at here is 12 layers of coil that are built up. These layers are printed, they're very, very thin because the printer is able to deposit very thin layers of material. And essentially what you get here is an entirely new way of making a electrically functional part, in this case a coil, which actually I can plug in. One thing that I want to show you is that it's not working as a magnet now when it isn't plugged in, but if we then connect that to a power source as follows, we'll give it a couple of seconds to warm up. That little magnet there is then something that you can pick up with the electromagnet, and it's fully functional as you'd expect it to be. Now obviously some people are very suspicious and think there's probably another magnet hidden inside there, so I will demonstrate what happens when you disconnect it, and you'll see that this is being driven by the electrical magnet rather than some other sneaky circus trickery. So what you see here is something you could essentially uniquely do with 3D printing. So we've printed in a geometric pattern here in order to enable this rigid polymer to have mechanical properties that you wouldn't normally be able to get out of rigid plastic. So it's maintaining that thickness of part all the way through, a little bit as you might do with, say, CNCing into wood or metals to allow them to flex. So this is one way of bridging the gap between rigidity and flexibility in a part. So following on that theme of flexibility, so one way, as we just saw, is printing in geometries into the polymer, and this part actually uses a slightly different technique where you might be able to make out the taper here in that polymer. So there's a mechanical strain relief. Essentially you go down from a thicker rigid part of the board, which over here you can see is also the bit where you'd be able to, say, solder parts, or even in this case into those cavities you could embed the parts as well. And because of that strain relief going through, as the part gets thinner, it goes from being rigid to being flexible, and you can tune the amount of bend or flex you want to get in this part of the component by adjusting its thickness in your part design. So you can do both rigid and flexible. You can certainly use this, for example, in bend to fit type applications, where you might want things to fit into a smaller constrained space, and you can adjust the fit not just in terms of size but mechanical properties as well. So this little trinket is an example of what you could call an MID, like a molded interconnect device, along the lines of the way in which the antennas in most smartphones today are made, where you will need a topography to get the most out of your circuit, in order, for example, with antennas, to get that benefit of a three-dimensional antenna. Essentially what you're seeing here then is there's a right angle, which is the kind of shape in the conductor that you might associate with a traditional circuit, but you can also see, of course, that because we're printing, we can print in curves. If I turn the part over here, what you'll see as we make that journey, first you can see the metal within the polymer, and you can obviously contour and shape that surface in such a way as to either have the metal exposed, which is really what you do with a traditional MID, where you'd be adding those conductive traces to the surface of a molded part, This particular approach, the Dragonfly approach, enables you also to have those traces within the polymer, so you can envision things like a multi-layered MID device, which allows you to create objects that really wouldn't be manufacturable.